Is here live at the Brian Cox tour. The majority of people, if not everybody I suppose, believe in the heliocentric model. Of course we'll be trying to get a question from Brian on that stage later on, and possibly we'll be asking some people here if they really believe in a spinning board. I'm here with Gempanda. Say it, not on camera, just say hello, Gem.
Hello. Okay. Good evening, everyone.
Yeah, where are we?
We are at Derby Arena. We're going to see Brian Cox live, and Chemo is going to learn all about the secrets of the universe.
We're going to learn
and abandon his flat earth belief forever.
We're going to learn something tonight. We're going to find out if what we've been told is actually true. Should we go find our seats? Let's do that.
Let's do that.
Dispel the mystery of existence. If we take everything into account, not only what the ancients knew, but all of what we know today that they didn't know, then I think we must frankly admit that we do not know. But in admitting this, we have probably found the open channel. This planet is not terra firma. It is a delicate flower, and it must be cared for. It's lonely, it's small, it's isolated, and there is no resupply, and we are mistreating it. Clearly, the highest loyalty we should have is not to our own country, or our own religion, or our hometown, or even to ourselves. It should be to, number 2, the family of man, and number 1, the planet at large. This is our home, and this is all we've got.
February, and we've been all over the world since, but it's fantastic to be back here, so thank you for coming. Thank you. Science is the study of the universe at all scales, from atoms to galaxies. And I suppose at its simplest, in a sense it's the purest definition, it's an attempt to understand and explain things that we can see and answer very simple questions about the universe. So, why are planets spherical? Why is the sky blue? Why is the grass green? And so on. But there are undoubtedly deeper questions that are still scientific. Questions such as, did the universe have a beginning, or is it eternal? How did life begin on this planet? And is life rare or common throughout the universe? But then also, I think there are questions that seem at first sight to fall outside of the domain of science. And you heard one of them, in fact, in that introduction from the Nobel Prize-winning scientist Richard Feynman, when he said, what is the meaning of it all? I mean, that does not sound like a scientific question. But tonight, as I talk about those deep questions, the origin and evolution of the universe, the origin of life, and so on, I hope that there's an underlying message, if you like, an underlying idea, which is that if we want to ask those deeper questions, the meaning, what it means to be human, and so on, then science is necessary because it provides a framework within which we can answer such questions. It delivers ideas that we need if we want to answer those questions for ourselves. I mean, for example, if we want to know what it means to be human, we need to know where we are in the universe, and we need to know when we are in the universe. universe. And those are undoubtedly scientific questions. Take the first one. So where are we in the universe? And this image you've been looking at is, at first sight, I suppose it's not the most spectacular image in the history of astronomy. It's very beautiful. It's the Earth-Moon system, so the crescent Earth and the crescent Moon. It becomes more fascinating, I think, or powerful, if you know from where it was taken. It was taken, in fact, from Martian orbit by a spacecraft called the Mars Reconnaissance Orbiter, pointing its cameras not to the surface of Mars, but back towards its home world. And even from this distance, which is, Mars is usually the closest planet to the Earth, but even from this distance, I think you get a sense of what, again in the introduction, the astronaut Scott Carpenter said. I think it's a beautiful reflection on our position in the universe from, remember, a test pilot back in the 1960s, who was not really poetic until that moment, when he looked at the Earth from space and he said those words: the Earth is a delicate flower and we are mistreating it and it must be cared for. Beautiful passage. That perspective that altitude gave the astronauts, and you hear it from virtually every astronaut you hear speak about the experience of looking at the Earth from space. That perspective, I will also argue tonight, is delivered by the intellectual exploration of the universe, by the study of astronomy and cosmology. So there is a picture, an image of our fragile world from Martian orbit. The next step out, if we want to answer this question, where are we in the universe, is to consider the size of a planet relative to the next largest object, if you like, which is a star. This is, again, an image. It's a movie, in this case, a film, taken by another spacecraft called the Solar Dynamics Observatory. Now, its job is to observe the sun. So it sits in space, watches the sun all the time. It's watching for solar flares, explosions on the surface of the sun, space weather that can affect communication satellites and so on. But on this day, as well as this magnificent image of the sun, it captured something interesting. I don't know if you can see, but just there. You see this little black blob tracing across the face of the sun. It'll come back on when it loops around. So there it is, little black dot. And that's the planet Mercury. So that's Mercury tracing its way across the face of the sun. This is called the transit of Mercury. One of the reasons I like it is the cosmic web. And it's telling us something, clearly. It's telling us about events that happened before there were stars and before there were galaxies. And we'll look later on tonight as far out into the universe as we can to see if we can observe what those events might have been in the far reaches of the past, before the stars and galaxies formed, that laid down this pattern in the sky. Now, surveys like this allow us to estimate the number of galaxies. And I emphasise each one of these is measured, and each one of these is roughly the size of the Milky Way, 200 billion, maybe a trillion suns, like the Whirlpool galaxy or the Pinwheel. Surveys like this allow us to estimate the number of galaxies in the observable universe, and that number is around 2 trillion galaxies. So that's the arena within which we do cosmology, and the challenge is to understand how that came to be here, from where did all this matter and energy come, and to understand essentially our place. I mean, I think immediately you can see that our place is not significant on this scale. The universe is very big all alone. But that's theoretical physics. That's what we have to do. Now, in terms of cosmology, in terms of understanding the origin and evolution of the universe, there is one theory, one theoretical structure that we use. And it's a theoretical structure we've had since 1915. We can date it precisely because that's the publication date of Einstein's theory of general relativity, which is the framework we use to do cosmology. And I wanted to spend a few minutes explaining that theory, explaining where it came from and how it describes the universe, because later on I want to use it to explain in particular black holes, which are some of the most fascinating, least well understood and violent objects in the universe. The theory itself, as I said, it published in 1915. Actually, the foundations of it go back to 1905, and something called Einstein's special theory of relativity. It began life, interestingly, as a theory of space and time. But that's a weird thing to say, a theory of space and time. Why would we need such a thing? It then became a theory of gravity in 1915, 10 years after it was published, and then became a theory of cosmology, which is a theory of the universe. So I want to describe in a little bit of detail how that happened, because there are a series of things I said there which are quite surprising, I think almost shocking things to say. Now let's start with the first one, a theory of space and time. Why do we need such a thing? If you go back to Newton, back 1687, the Principia Mathematica, the founding document of modern physics from which F equals ma and all that stuff comes, right? Line 1 almost, page 1 of Newton's Principia, there is a statement which Newton writes down, which is, I assume that time is universal. And line 2 is, I assume that space is universal. What did he mean? Well, at time, I think he meant what we all think of time as being like. Right? So if we all synchronised our watches and they were perfect watches, and we wandered around for a year or two and came back here in 2022 or something, and looked at the watches, they would read the same time, because time ticks at the same rate for everyone in the universe. That's what we imagine time is. And then space being universal, well, that's the idea that the universe is a big box within which things happen. So what is space? It's the distance between things and so on. It turns out both of those ideas are not correct. And Einstein was the first to take that idea seriously and therefore build a new picture of what time and space are, which is the key to understanding gravity and ultimately cosmology. How did he do that? Well, back in the 1860s, and actually back even before then, when people like Faraday and Ampere were doing experiments in electricity and magnetism, it was discovered that, first of all, light is an electromagnetic phenomenon, which means it's got something to do with electricity and magnetism, and secondly, it behaves in a very strange way, which is it moves through the universe at a constant speed, no matter how you look at it, no matter how you observe it. Now this is very counterintuitive, it's a strange thing. We discovered it by a combination of experiments on bench tops essentially, and then doing some theoretical physics, some mathematics. But it was strongly suggested that light behaves in this way. It's called a constant of nature. So for example, the idea is if I ran towards you now, let's say I run towards you at, I don't know, 3/4 of the speed of light, and switch on the torch. The light sets off from the torch and it passes by your head at the speed of light, not 1.75 times the speed of light or something like that. So it doesn't behave like any other thing in the universe. Now, Einstein was the first to take those experimental ideas, it's nature talking to us, saying this is the way the world is. He was the first to take that seriously and to work out what it implies. He did that through a series of what's called thought experiments. And I wanted to show you one. The thought experiment Einstein used is called a light clock. So the light clock, I've drawn it here, it's essentially two mirrors, and the pendulum of the clock would be a beam of light that bounces up and down between the mirrors. So you can see that it moves very fast, 300,000 kilometers a second, and it bounces up and down, and that would be a very accurate clock. You count the bounces, if you like, and you work out the time. And then Einstein said, well, okay, what happens if I take that clock and I move it? So let's imagine I have the light clock on the stage, and I'm going to walk across the stage and carry it across. So you're going to sit there and you sit still and you watch it. What does it look like to you? Well, if I carry it across the stage, then you would see what I've drawn here, which is you would see the light beam sweep out that triangle, the white path, because I'm moving the clock. So it goes in a triangular path across the stage. But remember, we've decided, we've agreed, because nature told us that we all agree on the speed of light, no matter how we're moving, how we're observing it. So that implies something very shocking indeed, because you see, from the stationary clock, the light bounces up and down like that. So one tick would be up there and back down there again. The moving clock, up there and back down there again. Now this path here is obviously longer than that path, but the speed is the same. Therefore, the moving clock has to take longer to tick. The light has to take longer to go along there because it's moving further at the same speed. The moving clock runs slow. So this is a shocking result, right? I actually teach this at the University of Manchester. I'm teaching it in about 2 weeks' time to first-year undergraduates. And when I say this, I think half of them think I'm sort of bullshitting a bit, because they think there's some sleight of hand in this explanation, but there isn't. So I hope you can see, if we accept the speed of light as a constant, on which we all agree, it follows that time does not behave how we think, because the moving clock ticks more slowly. So time passes more slowly for moving objects relative to stationary ones. And that means time. So it's not just this clock, it really means now, as I move across this stage, because I'm moving relative to you, time is moving a bit more slowly for me, from your perspective. So my cells are aging at a slower rate. It really is a property of time, and not a property of this strange clock. Time is not universal. It's relative. It depends on the observer doing the measuring. That's the first thing that Einstein realised. Similar arguments, which I won't go into because we want to get out of here tonight at some point, suggested to Einstein that space as well was not absolute. They related ideas, in fact. And so what Einstein did, first of all, 1905, 1906, 1907, was to replace our notions of absolute time and absolute space with something else. And I want to describe the something else, because the something else is the basis of cosmology. The something else is an idea which at first sight doesn't sound too radical. It's an idea called space-time. So we just merged the two together. And it's often described as something called the fabric of the universe, space-time. They're not independent things. They're woven together into a kind of, almost like a structure, if you like. And that structure is the universe. Space and time woven together, the fabric of the universe. I've sort of drawn it here. So I've drawn space across the horizontal axis and time up the vertical axis. So this is a diagram, if you like, of everything that happens. This is the past down here, the present along here, and the future up there, and all of space, which we could represent along here. And space-time is often also described as the collection of the set of all events, all things that happen. So what's an event? Well, for example, this morning your alarm clock may have gone off in your bedroom, so that's an event in space-time. It happens somewhere and somewhen. And tonight, you go to bed, you'll turn the light switch off, that is another event. It's something that happens somewhere and somewhen in space-time. So on a diagram like this, I could point out, plot all events that have happened in the universe, are happening, and will happen in the universe. And I could draw them on a diagram like this. Now, to make this more specific, because Einstein's theory is about the different relationships between things that happen, which is really what science or physics is. Let me describe some events that happen to me. So we could all imagine that we could all think about these events in our lives. So let's say that this point here, which I've just drawn in the origin of our graph of space-time, let's say that's my birth, right? That's me being born. March the 3rd, 1968. It's an event. I've got a photograph just after I was born. So we can all imagine that event in our lives, the moment we are born. Let's say I put it there on my space-time diagram. Then let's go into my future. So we'll trace the events of my life, and let's stop, let's say Christmas 1974, because I had a photograph of it, so there it is. So I'm just about, 5, 6 years old, something like that. That would, on our diagram, be in the future than my birth, so it'd be somewhere up here, and perhaps a slightly different place. I was born in Oldham, and that's a slightly different place, actually, in a place called Middleton. So let's put it there. So it's forward into the future, and a slightly different place in space. Then we can move forward again. So in my life, let's go, because I had a picture of it, to the 1980s, so you know what's coming. There we are. Me in the 1980s, in a band called Dare. There I am. And this would be in the future again, into the 1980s, and a different place. This was actually in Berlin, I think. So we plot that there, let's say. And let's come closer to the present day, let's say over here, which would be me filming with the BBC on Easter Island a few years ago. So 4 events in my life. One of the reasons I chose that, by the way, is a friend of mine pointed out that if you look at the way that I'm standing in 1974 and the way that I'm standing on Easter Island, it's bizarrely exactly the same. It's a very strange stance. that I've always adopted for my whole life. People say that I stand in a stupid way on top of volcanoes on telly. I don't, I've always stood like that. It's nothing to do with telly. I don't know. Anyway, there we are. So 4 events in my life. Events in space-time on the space-time diagram. Now, there is a central concept in relativity which really drives home the strange nature of the theory, and it's quite a beautiful concept as well. If you draw the line through all the events in your life, so you imagine these, your birth and your Christmas when you're young and so on, all the way to now when we're here in Derby in this arena, plot them all out in a diagram, join them all up. So I do that for my life there. This is called a world line, a world line. And we all have world lines. They're individual to each of us. As you can see, they trace out the events, all the events in our lives, from our birth to the present day, and then onwards to our death, actually. The whole thing traced out in space-time. Now, the interesting idea, the central idea, I would say, in relativity, is that the length of this line has a meaning. It is a real thing that we measure. So the length of the line, what is it? We measure the length of this line through all the events. The length of that line is the amount of time that you have experienced. So if you had a perfect watch and you set it going when you were born and carried it with you for your whole life to tonight, and you look at the time it reads, that's your age, what that actually is a measurement of in this theory is the distance you have travelled over space-time. Now, that's a nice idea. It has a profound consequence though, and I can show you that by drawing another world line. So this is my mum's world line. So it starts in the past, back in the 1930s, and she experiences all the events in her life. That obviously were at the same place in time and space when I was born, and then off we go. She would have stayed with me for most of my early life, and then perhaps I'd have gone to school and she goes to work and so on. So she experiences different things without me. And then let's say that point there, that event is Christmas last year when we were together having Christmas dinner. Now, if you ask the question, well, how much did she age from my birth to Christmas dinner last year, and how much did I age? That's the length of the world line. And the world lines are different lengths because we experience different things. Now, it's greatly exaggerated on this diagram, but that has the implication that we aged at different rates. So really, in this theory, your time is personal to you. And really, if you are with friends now, when you go off and you agree to get together next weekend, let's say, for a drink or whatever, then because you experience different things, you take a different path between these two events in space-time, and so you age at different rates. And I can show you what that is by just sticking 3 lines on it, and these grey lines and the red line. You see that what these do now, there's a guide to the eye, is they divide up this space-time into 3 regions. There's a region inside these grey lines, and then these 2 regions outside. Look what happens if you go into this region here. Then remember what these are. These are tracing out the whole bit of space-time that can be accessed or influenced by an event. So this one here, for example, it could talk to or access anything in here, but nothing outside. This one could talk to anything in there, but nothing outside. Same for this one, anything in there, nothing outside. So anything that goes into this region can't get out, because it can't ever influence anything outside the region. It would have to send a signal faster than the speed of light to get out into the rest of space-time. So this is kind of a region that's cut off from the rest. Also note that these cones are all tilted towards this red line in the middle. Now, what are these cones? Well, one way to think about it is they're marking out the accessible future of every event, because everything that this thing can influence or experience is inside this cone. And all futures point to this line here. So this line is called a singularity. It's it's the end of time in this region, the point to which all futures point and end, the singularity. And these lines here are called event horizons. Why? Well, obviously, because any event that happens in here cannot get out. Anything that goes in can't get out. So these are like a horizon dividing up the space-time. So this is, of course, a picture of a black hole. It's something that we know now exists. And I'll talk about that actually in the second half of the show. But we've known theoretically they could exist for a long time. One way you can make this geometry of space-time is to take a big star at the end of its life, it runs out of fuel and it starts to collapse. And no known force for the largest stars can hold it up. So it collapses and collapses and collapses until, in a sense, it winks out of existence. It all collapses to a point, which is the singularity, and it leaves this imprint of its existence in the fabric of the universe, which is what we call a black hole. Now, we don't need to just visualise it with this diagram, because when I was putting these shows together, I was introduced to a graphics company called DNAG, and DNAG did the graphics for the film Interstellar. So if you've seen Interstellar, you'll know that the black hole is a central character in the film. And the director, Christopher Nolan, didn't want to just have an artist in of these stars, other than just the fact that we're in orbit, is caused by the predicted distortion in space and time caused by that dense object, the black hole. There are some obvious things that you can see in the simulation. First thing is I suppose what you might call the black hole itself. This is actually in part the event horizon, but it's actually bigger than the event horizon. It's called the shadow of the black hole on the star field. The reason it's a bit bigger is that if you imagine, let's say there's a beam of light coming from your eyes, and let's say you're looking above the black hole, so your eyesight's going above, past the event horizon, to the stars behind. But that beam of light can curve around and hit the rear side of the black hole. So in other words, you can see the rear of the black hole as well as the front from your vantage point in your spaceship. So you see the whole 360 degrees of the black hole, and that's what you see as the shadow. It's interesting also in this simulation to note that it's very bright around here. Why is that collection of stars around the shadow itself? That's, again, if you imagine that you're in a spaceship now, there are stars behind you, and the light from those stars is coming along, is going around the black hole, and it's actually being curved all the way underneath and back out to your eye again. So you see all the stars that are behind you, as well as the stars that are in front of you, and the light being reflected by the black hole. So you in fact see the whole universe as you see it mapped around here, actually technically an infinite number of times. So you see the whole 360 degrees of the star field. And just one more thing, this is very obvious, this sort of ring around the black hole where the stars are going in funny directions, that's called the Einstein ring. And what that is that if you imagine a star from your vantage point right behind the black hole, so look straight through the centre of it, there'll be a star behind it, and the light from that star is deflected sort of at all angles around the black hole, below it, above it, and to the side, and so you see an image of that star in a big ring around the black hole, the star on a line between your eye and the centre of the black hole, and that's what you see as the Einstein ring. So you see, we could talk about this all night. There's all sorts of distortion going on, but that's the basics of the distortion in space. But there's